Hi everyone, welcome to Go Classes. In this session, we are going to discuss some important points about 3NF and BCNF decomposition. So let's start. Let's start with this question. Which of the following statement is true? Read these two statements and tell me which of them is true statement. Let me know. The first statement is 3NF decomposition is always lossless and dependency preserving. The second statement is BCNF decomposition is always lossless and dependency preserving. So which statement is true? The answer is this is also not true, this is also not true. Both are actually false. Both the statements are false. Now, if you think that this statement is true, this statement is false, then there is a misconception. Okay, so I want to discuss this misconception in this session. So I hope you understood the importance of this session. What I actually want to discuss in this session, some important points about 3NF and BCNF decomposition. Okay, so remember, this statement is also false. This statement is also false. The first statement is saying 3NF decomposition is always lossless and dependency preserving. This statement is actually false. We will see. Don't worry, we will see. Okay, so I'm going to discuss about this misconception and I will also give you the correct concept. Also, I'm going to solve each and every gate question based on this concept, or I can say based on this misconception. Okay, so I'm going to solve each and every gate question. Now let's start. I hope you know about these two DBMS books. This is a DBMS book by these three authors, and this is another DBMS book by these two authors. Okay, so let me tell you, to get clarity on this misconception, because I want to tell you the clear and correct concept. So what I did, I sent a mail to all these three professors and also to both of these professors. Okay, so to all of them, I sent a mail. You can see, to get a clarity on this misconception, I mailed Professor Korth, I mailed Professor Korth, Professor Sudarshan, Professor Nawate. Okay, all of them I mailed and got their reply as well. Okay, so I want to thank all of them for their response. Now let's see. So you can see this was their reply. You can see this is the reply from Professor Sudarshan. You can see this was the reply. Yes, you are right. Okay. So I will tell you, don't worry. You can see. Also, you can see this is the reply from Korth, from Professor Korth. Again, you can see a positive reply. And this was the reply from Professor Navate. Again, here also you can see. So I will discuss, don't worry, I will discuss all of these replies. Replies also I will discuss. But before that, I want to thank all of them for their response. Okay. They took time from their busy schedule and they replied to my doubt, to my DBMS doubt. So from the bottom of my heart, I want to thank them for their response. Okay. Now let's see. So let's start with this with some basic concepts. First of all, if you have a set of relations in a database, if you have some set of tables, then how can you say that this set of tables is in BCNF? In your database, you have, let's assume, 4 relations. Then how can you say that your database is in BCNF? Very simple. Each relation must be in BCNF, right? Yes or no? Okay, so very simple point, that this set of relations, this database will be in BCNF if every if each relation is in BCNF. That is very simple, that you already know. Now, so you can see, if I give you a database, there are multiple tables, there are multiple relations in the database. Now this database will be in BCNF if every relation is in BCNF. If every individual relation is in BCNF, R1 is in BCNF, R2 is in BCNF, and so on. Similarly, if I give you database, and this database will be in 3NF if every individual relation is in 3NF. Similarly, this database will be in 2NF if every individual relation will be in 2NF. Okay, so this is a basic concept that you already know. Now let's see this. If your relation is not in BCNF, then what you can do? If your relation R is not in BCNF, then how to make it into BCNF? Very simple. You will decompose this so that every sub relation will be in BCNF. Yes or no? Very simple. What you will do? You will decompose this relation R into sub relations such that each sub relation is in BCNF. Correct? So far, every concept is clear, right? Okay, one by one, every simple small point I am discussing. So if your relation is not in BCNF, then what are you going to do? You will decompose this relation R into sub relations such that every sub relation is in BCNF. Okay, so very simple point. This is about BCNF decomposition. Now let's see this. You have a relation R ABCD, and these are the functional dependencies. So tell me about this question. Consider the decomposition R1 A comma B, R2 C comma D. Is this a BCNF decomposition? Look at this decomposition and tell me, is this a BCNF decomposition? Let me know. This relation R, first of all, you tell me, is this relation R in BCNF? Look at this relation R and tell me, is this in BCNF? What is the candidate key here? The candidate key, that is AC. Yes or no? AC is the candidate key, and this is not in BCNF. This relation R is not in BCNF. Okay, so what I'm doing, I'm doing a decomposition of this relation R. This relation R ABCD, I'm decomposing R1 AB, R2 CD. So this is the decomposition. Now tell me, is this a BCNF decomposition? Tell me, is this a BCNF decomposition? The answer is yes. The answer is yes. Yes, this is a BCNF decomposition. Why? Because you can easily see that this subrelation is also in BCNF and this subrelation is also in BCNF, right? Okay, yes or no? This is also in BCNF. This is also in BCNF. Actually, you don't even have to check. Why? Tell me. Because every relation with the two attributes is always in BCNF. Yes or no? That you already know. Okay. In our lectures, we have already seen. So we know that every relation with two attributes, okay, with at most two attributes, every relation with at most two attributes is always in BCNF. Correct? Okay. So very simple point. So you can easily see this R1, this is in BCNF, R2, this is in BCNF. So is this a BCNF decomposition? The answer is yes. Okay. But tell me one thing. You might be thinking, sir, this is lossy. Yes or no? This is lossy. Yes, I agree, this is lossy. See, this is BCNF decomposition, that is correct. But yes, this is lossy also. I know this is lossy because R1 intersection R2, that is phi. There is nothing common. Yes or no? See, there is nothing common in R1 comma R2. The set of common attributes, that is basically phi. Okay. So yes, this is lossy. Agree with me? So, but remember, is this a BCNF decomposition? This is my question. Please don't confuse between these two questions. I am asking, is this BCNF decomposition? The answer is yes. Is this lossy? The answer is yes. Is this dependency preserving? Is this dependency preserving? Please tell me. Is this dependency preserving? The answer is yes. Okay, this is dependency preserving. So please notice one thing. These are three different questions, right? Are you understanding my point? That, see, if I ask you, is this BCNF decomposition, then what you will check? I tell you that is this decomposition, is this BCNF decomposition, then what you will check? You will check each sub-relation. Okay, you will check that this should be in BCNF, this should be in BCNF, and that is correct. This sub-relation is in BCNF, this sub-relation is in BCNF, so this decomposition is BCNF, that is correct. But yes, this is lossy. Also, this is dependency preserving. Okay, so very simple point. Okay, you already know every relation with at most two attributes, that is always in BCNF. Okay, now tell me about this question. The same decomposition, is this 3NF decomposition? The same decomposition, can I say this is 3NF decomposition? Again, the answer is yes. Again, the answer is yes, because this sub-relation, this is in BCNF. Every BCNF is 3NF. Yes or no? So this is in 3NF. Okay, if a relation is in BCNF, then that is in 3NF also. You can see this is also in 3NF. Both are 3NF. So I can say, yes, this is a 3NF decomposition also. But again, you can see this is lossy. I agree, this is lossy. Okay, also this is dependency preserving. This is dependency preserving. Okay, is this clear? So now you notice one thing. What is BCNF decomposition? What that actually means? BCNF decomposition, that simply means the decomposition in which every subrelation is in BCNF. Is this clear? And 3NF decomposition, what it means? It simply means a decomposition in which every subrelation is in 3NF. Okay, very simple point. Now tell me the answer for this question. Every BCNF decomposition is lossless. From the previous example, you can easily see that this statement is false. Yes or no? From the previous example, you can easily see. We have already seen this example where we have a BCNF decomposition, but that is not lossless. That is lossy. So every BCNF decomposition is lossless. That is false. Okay. Is this clear? Next, tell me the answer for this question. Every 3NF decomposition is lossless. Again, that is false. Okay. Now, let's see this. So what are the true statements? What are the true statements then? These are the true statements. You can see for every relation, there exists a 3NF decomposition which is lossless and dependency preserving. See, these are the true statements. You can see for every relation, whatever relation you take, there always exists a 3NF decomposition which is lossless and dependency preserving. So understand the difference between this statement and this statement. Here we are talking about every. Okay, here I'm saying every 3NF decomposition is lossless. This is false. Okay, but remember, for every relation, there exists a 3NF decomposition which is lossless and dependency preserving. This is true. Now, is this point clear? So far, if there was any confusion, then now did you understand the point? The important point, let me know. So you can easily see for every relation, there always exists. We can always find some 3NF decomposition, some decomposition in 3NF, which is lossless and dependency preserving. Similarly, for every relation, there always exists a BCNF decomposition, a decomposition in BCNF that is lossless, but there is no guarantee of dependency preserving. Okay, so very simple point. For every relation, there is a guarantee we can always find at least one 3NF decomposition which is lossless and dependency preserving. And for every relation, there is a guarantee there always exists a BCNF decomposition, a decomposition in BCNF that is lossless, but there is no guarantee of dependency preserving. It may or may not be dependency preserving. Okay, these are the true statements. I hope this point is clear. So now tell me the answer for this question. For a database relation R, which of these statements is true? Every 3NF decomposition is lossless. Some 3NF decomposition is lossless. This is correct. Whatever database relation you take, you can always find some 3NF decomposition, some decomposition in 3NF, which is lossless. This statement is true and this statement is false. Okay, is this clear? Let me know. Tell me the answer for this question. For a database relation, every 3NF decomposition is lossless and dependency preserving. This statement is false. But for any database relation, some 3NF decomposition is lossless and dependency preserving. This statement is true. Okay, is this clear? Very simple. Tell me the answer for this question. For any database relation, every BCNF decomposition is lossless. That is false. But some BCNF decomposition is lossless. Some decomposition in BCNF that is lossless. That is true. Okay. Tell me the answer for this question. For any database relation R, every BCNF decomposition is lossless and dependency preserving. This is false. Okay. And some BCNF decomposition is lossless and dependency preserving. This is also false. Okay. Here both are false because, as I told you, that there is no guarantee of dependency preserving. There is no guarantee of dependency preserving for BCNF. Is this clear? Okay. For any database relation, remember, there is a guarantee. Some decomposition in BCNF will be lossless, but it may or may not be dependency preserving. Okay, is this clear? So in this case, both are actually false. Is this point clear? Tell me, let me know. Now let me discuss. First, let me discuss all the important points about 3NF decomposition. Then I will discuss all the important points about BCNF decomposition. But so far, is everything clear? The point that I'm trying to tell you, is that point clear? Please tell me. Are you understanding the difference between every and there exist? Let me know. Now, let's see all the important points about 3NF decomposition. I will not discuss the decomposition algorithm. I am not going to discuss 3NF decomposition algorithm because that we have already seen in our lectures. I will put the link in the description so you can check it out. Okay. So let's see. For 3NF decomposition, we have this algorithm, synthesis algorithm. Yes or no? In our lectures, we have already seen this synthesis algorithm. A lot of practice we have done. So for 3NF decomposition, we have this algorithm, this synthesis algorithm we have, or you can say 3NF synthesis algorithm we have. And what this algorithm will do? See, if you apply this algorithm, if you apply this particular algorithm for 3NF decomposition, then this algorithm will give you a guarantee. Then this algorithm will definitely give you a lossless and dependency preserving 3NF decomposition. You can see, if you apply this synthesis algorithm, if you apply this 3NF synthesis algorithm, then there is a guarantee. There is a guarantee that you will get lossless dependency preserving decomposition into 3NF subrelations. Okay, is this clear? Very simple. So this algorithm will always give you a lossless dependency preserving decomposition in 3NF. Very simple. So very simple that this synthesis algorithm, this will always give you a decomposition which will have these three properties. On any relation, you take any relation R, any database relation R, if you apply this synthesis algorithm, then you will get a decomposition you will get which will have these three properties. All these three properties will be there. It will preserve the dependencies, dependency preservation will be there. It will be lossless join. Another name is non-additive join. Okay. Also, all the sub relations will be in 3NF. Okay. All the resulting relations will be in 3NF. So very simple. If you apply this algorithm, then all these three properties you will get. Okay. Is this clear? Let me know. But one more thing I want to tell you. See, this is about the algorithm. If you apply this algorithm, all these three properties you will get. But if you randomly do something, if you randomly do some decomposition in 3NF, then we don't know whether we will get all these three properties or not. Are you understanding my point? If you, for any relation, for any database relation, if you apply this algorithm, there is a synthesis algorithm. In our lectures, we have already seen this 3NF synthesis algorithm we have already seen. The link I will provide you in the description so you can check it out. You can watch it if you don't know what is synthesis algorithm. But if you apply this algorithm, then we will always get this type of decomposition which will have all these three properties. Okay, but if you don't apply this algorithm and if you randomly do some decomposition, then it is not mandatory that you will get all these three properties. Okay, is this clear? So you can easily see the synthesis algorithm for 3NF. Very simple. You can decompose a relation. Any relation you take, you can decompose such that all these three properties you will get. The decomposition will be in 3NF, the decomposition will be lossless, and the decomposition will be dependency preserving. Did you notice one thing? These three things are separate. Okay, the decomposition you will get in this synthesis algorithm, the decomposition that you will get, it will have all these three properties. So these are three different properties, but this algorithm will give you a decomposition with all the three properties. Is this point clear? Very simple. So you can see for all relations, for every relation, it is always possible. Okay, it is always possible to get all the three properties. Okay, so very simple, 3NF, also lossless, also dependency preservation. Okay, so this is always possible. For every relation, there exists a decomposition in 3NF, which is lossless and dependency preserving. Okay, so very simple point. So you can see for all relations, lossless 3NF decomposition is always possible. That is correct. For all relations, lossless dependency preserving 3NF decomposition is always possible. That is also correct. Okay. Is this clear? Simple, right? So very simple. Here you can see that every relation has a decomposition in 3NF which is lossless and preserves the functional dependencies. This is the final theorem. This is the final result. Okay, every relation has a decomposition in 3NF which is lossless and dependency preserving. Okay, is this clear? Has a decomposition. This type of decomposition always exists. For every relation, this type of decomposition definitely exists. Now let me tell you all the important points about BCN of decomposition. Now let's see. For BCN of decomposition also we have algorithm. Yes or no? So there is an algorithm for BCN of decomposition also. In our lectures, we have already seen this BCN of decomposition algorithm. But this algorithm, what this will guarantee? This BCN of decomposition algorithm, this will guarantee lossless decomposition in BCNF. Okay, so you can see this BCNF decomposition algorithm, this will guarantee lossless decomposition into BCNF subrelations. Okay, very simple, right? But remember, there is no guarantee of dependency preservation. Actually, there are some relations for which there is no decomposition in BCNF which is dependency preserving. Okay, see this. There are some relations for which these three properties we can never get. Okay, read this line. There are some relations for which there is no way, for some relations, there is no way to get all the three properties BCNF, lossless, dependency preservation. There are some relations for which these three properties we can never get together. Is this clear? Okay, there is no way to get all of them together. Let me know. So this is the point. There are some relations, remember, for which there is no way to get all these three properties together: BCNF, lossless, and dependency preservation. Okay. So these are the points. These are the conclusions that for all relations, for every relation, you can get lossless BCNF. That is always possible. Okay. Lossless BCNF is always possible. Okay. But lossless dependency preserving BCNF, that is for some relations that does not exist. Okay, for some relations that does not exist. So remember, for some relations, lossless dependency preserving BCN of decomposition does not exist, but for other relations this will exist. Okay, tell me, can I say that for every relation lossless dependency preserving BCN of decomposition is not possible? Tell me, can I say that for every relation, these three properties you can never get? No, 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 no. Remember, for some relations, you cannot get these three properties. Okay. But for other relations, for some relations, you can get all these three properties. Okay. Is this clear? Very simple point. So now let's see the summary. Let's see the final summary. So far, what we have seen, let's see the summary. Now, decomposition to BCNF. Remember, we have this algorithm which will give us lossless BCNF decomposition. This type of algorithm we have. Okay. And let's see this decomposition to 3NF. There is algorithm, synthesis algorithm, 3NF synthesis algorithm. There is algorithm for lossless and dependency preserving 3NF decomposition. Is this clear? So remember, for every relation, it is always possible. For every relation, it is always possible to decompose into 3NF such that it will be lossless and dependencies will be preserved. Okay, for every relation, this is always possible. I am talking about the possibility. For every relation, this is always possible to have a decomposition which will be in 3NF and lossless and dependency preserving. Okay, but remember, for BCNF, what will happen? You can see it is always possible to get decomposition into BCNF which is lossless, but it may or may not preserve the functional dependencies. It may or may not preserve functional dependencies. Okay, is this clear? Let me know. Now, finally, did you understand why these two statements are false? Please tell me. Now, read these two statements. 3NF decomposition is always lossless. This statement is false. But there exists a 3NF decomposition which is lossless and dependency preserving. That is true. Are you getting my point? See, very simple. If I give you a relation R, okay, let's assume you have this relation R. Now, for this relation R, you have many decompositions. Decomposition D1, decomposition D2. Okay, there can be many decompositions. For this relation R, you can have many decompositions. Okay. Now, at least one decomposition will always be there. At least one. There can be many more, but at least one decomposition will be there, which is in 3NF also, which is lossless also, which is lossless also, and which is a dependency preserving also. Okay, is this clear? So for every relation, there always exists a decomposition which has all these three properties. Okay, but remember, maybe this decomposition is in 3NF, but maybe this is lossy. Okay, it might be possible this is lossy. It might be possible, yes or no? Agree? Maybe this decomposition is 3NF, and maybe this is lossless also, but maybe this is not dependency preserving. Okay, are you getting my point? But the point is, this type of decomposition always exists. Is this clear? Let me know. Are you getting my point? So I hope you are understanding the point. Okay, similarly, remember, for every relation, there exists a decomposition in BCNF which is lossless. Okay, but remember, for some relations, there are some relations for which there does not exist any decomposition which is BCNF lossless and dependency preserving. There are some relations for which there is no decomposition which can guarantee all the three properties. Okay, but these two properties, these are guaranteed. Okay, for every relation you can get a decomposition which will have these two properties, that is guaranteed. I hope you got this point. I hope you understood this point. Let me know, is this point clear to everyone? See, to get the clarity on this doubt, I sent a mail to many professors. You can see. So this was my mail. You can see I was asking basically two statements. One is 3N of decomposition is always lossless and dependency preserving. This was statement one. And another statement is there is always a 3N of decomposition which is lossless and dependency preserving. Okay, so actually the statement as2, that is true. Statement as1 is false. You can see this is the reply from Professor Sudarshan. You can see, yes, you are right. There are decomposition which are lossless but BCNF. Okay, for example, you can see this example also they have given any decomposition into binary relations. Basically, if I give you any relation, what you do, you just give a decomposition with two attributes, two attributes, two attributes. Then automatically what will happen? This will be BCNF, this will be BCNF, BCNF, BCNF. But this may be lossy, yes or no? This may be lossy. Do you agree with me? So you can see, you can read this reply here. So you can see, yes, you are right. There are decomposition that are lossy, but in BCNF, any decomposition into binary relation, okay, very simple. So this is the reply. This is one reply. Another, you can see, this was my doubt, DBMS doubt. I sent a doubt, and this was reply from Professor Korth. Okay, you can see here that our statement was about 3NF algorithm, not about all 3NF designs. Okay, see, when you read this statement that you will get the decomposition which is in 3NF and lossless and dependency preserving, then this statement is basically about the 3NF algorithm, not about all the 3NF designs. For example, you can see this, read this statement. Consider a schema ABCDE. Okay, this is the reply from Professor Korth. You can see, consider a schema ABCDE, some set of non-trivial functional dependencies. The following is a 3NF decomposition. Look at this. The following is a 3NF decomposition, 5 separate schema. Okay, just put single attribute A, B, C, D, E. Okay, just put single attribute. Of course, this is useless because you can see this is not lossless. Actually, this is lossy. Also, this is not dependency preserving. You can see this is not lossless. This is not dependency preserving. Okay, informally, this is totally useless. But you can see this is also a 3NF decomposition. Is this clear? The following is also a 3NF decomposition. Okay, but this is actually totally useless. This is not a good design, right? Yes or no? Okay, this is not a good design because a good design must be lossless. Okay, a good design must be lossless and dependency preserving. That is a good design. But here, I hope you understood this. Okay, so this was reply from Professor Korth. Or the same thing is actually written. This reply from Professor Korth, this similar thing is actually written here also. You can easily see in the Ullmann book. Okay, if you study the Ullmann book, the same thing is written. You can see, if you want BCNF decomposition, then perhaps all we need to do is break the relation into two attribute subset. This will surely be in BCNF. Okay, yes or no? Whatever relation I give you, if you want BCNF decomposition, then all you have to do, you can see here, perhaps all we need to do is just break the relation schema into two attribute subset. The result is surely in BCNF. However, However, this type of relation, this type of decomposition will not satisfy the lossless condition. Okay, so you can see this is given in the Ullmann book. Also, you can see here that another reply from Korth, Professor Korth. Okay, you can see, right, my example, the example that Professor Korth gave, my example is in every possible normal form, but but offers no useful properties. Okay, you can see this is reply from Professor Nawate. Okay, see, this is actually another very interesting reply, because here Professor Nawate is talking about good good design. See, if you read the Nawate book, this screenshot is taken from the Nawate book. Okay, so in the Nawate book also, you can see they are talking about good database design. Okay, there are, so you can see a good database design. Okay, here you can easily see that another goal is to have each individual relation in BCNF or 3NF. Okay, we want every individual relation in BCNF or 3NF, but if you don't care about the lossless property and dependency preserving property, then that is not a good design. If you read the entire, here you can see it gives spurious tuples. It simply means it is lossy. Okay, so you can see, so here Nawate, Professor Nawate is talking about good database design. In the reply also, Professor Nawate is saying the same thing. Okay, you can see the problem with this question is that these words, BCNF decomposition and 3NF decomposition, these words are ambiguous. Okay, they should have said the correct theory of decomposition, the correct BCN of decomposition. Okay, means the good database design. You can see the good database design. You can here you can easily see. So read this. If they are talking about any decomposition, then you are right. Okay, but if they are talking about good decomposition, okay, I will tell you basically which question we are discussing here. This reply is for a NEELIT exam question. I will show you. Okay, this complete reply you can see S to S3. Okay, this is a reply for a NEELIT exam question. I will show you that question. Okay, then this reply will make more sense. Okay, so anyway, I hope you understood all these points. I hope everything is clear. Now let me tell you one more thing. In all the GATE exam questions also, this is followed. Okay, this same thing, this is followed in all the GATE exam questions also. You can see here, look at this GATE Computer Science 2005 question. In this question also, you can see, read option B. Is that true or false? See, option B is talking about the possibility, right? Yes or no? That lossless dependency preserving decomposition in 3NF is always possible. That is correct. Yes or no? Are you understanding? So you can see in the GATE exam also, they are talking about the possibility. They are talking about the possibility that this type of decomposition is always possible. That is correct. And this type of decomposition is always possible. That is wrong. Okay. So you can see in the GATE exam also, they are talking about the possibility. Are you understanding? You can see this GATE exam question. This is GATE 2019 question. Here you can see they are asking two separate questions. Okay, in this GATE exam question, there are two separate questions. One is they are asking for BCNF. BCNF is a separate question, and lossless and dependency preserving, that is a separate question. Are you understanding my point? So there are three properties. There are three properties. These are separate properties. BCNF is a separate property. Dependency preservation is a separate property. Lossless is a separate property. And in this question, they are separately asking for all these properties. Is this clear? Let me know. Okay. Similarly, you can see this GATE exam question, GATE 1994. Again, this is talking about there exist. Yes or no? Here you can see there exists a decomposition which has these properties. Okay. Again, this is talking about there exist. You can see this is GATE 2002 question. In this question, notice one thing. They are asking lossless. This is a separate question. They are asking dependency preservation. This is a separate question. And they are asking what the highest normal form. Actually, if you solve this question, let me tell you, the decomposition is BCNF. If you solve this question, you will find that the highest normal form will be BCNF, but actually you will check, I think either it is not dependency preserving or it is not lossless. Okay, you can check it out. But the highest normal form, that is BCNF. Okay, but remember here, this will not be dependency preserving. What I want to tell you, I want to tell you these are three different properties. They are separately asking. Yes or no? All the three different properties, they are separately asking, you can see. And this is GATE 2001 question. In this question, they are asking that for which relation does not have these three properties together. I told you some relations don't have these three properties together, right? Yes or no? Yes or no? I told you there are some relations for which all these three properties, BCNF, lossless, dependency preserving. I told you that for some relations, all these three properties are not possible together. Okay, this question is asking for which of these relations these three properties together are not possible. Okay, so all these questions we are going to solve, don't worry, but I hope you are getting the point. Okay, the point I hope you understand. So remember, BCNF, lossless, and dependency preservation, these are three different properties, these are separate properties. Okay, similarly 3NF, lossless, and dependency preservation, these are three separate properties. Now remember, for every relation, 3NF, lossless, and dependency preservation, these three properties we can get in some decomposition. For every relation, there exists a decomposition where these three properties we will get: 3NF, dependency preservation, and lossless. Yes or no? But remember, there are some relations for which these three properties we can never get together, which BCNF, dependency preservation, and lossless. There are some relations for which these three properties we can never get together, we can never get. Okay, we have to compromise with one of these properties. For every relation, these two properties we can always get: BCNF and lossless. For every relation, there is at least one decomposition, there exists a decomposition which is BCNF and lossless. Okay. Similarly, for every relation, there exists a decomposition which is 3NF, lossless, and dependency preserving. I hope all these points are clear. Let me know. Now let's solve all the GATE exam questions. Let's solve this GATE 2005 question. Okay. The question is saying which of the following statement about normal forms is false. Let's see the first statement. Is the first statement false? Let me know. BCNF is stricter than 3NF. This statement is actually true. What this statement means? Tell me what this statement means. BCNF is stricter than 3NF. That is correct, because you already know that every BCNF relation, these are the BCNF relations. Notice these relations are in BCNF. Every BCNF relation is in 3NF. So 3NF is more relaxed. Yes or no? 3NF is more relaxed. Every BCNF relation is in 3NF. But there are some relations which are in 3NF but not in BCNF. So you can see that BCNF is more strict. Yes or no? Is this clear? So BCNF is more strict. That is correct. Okay. Also, you can notice that BCNF does not allow transitive dependency on the prime attribute, but 3NF allows transitive dependency on the prime attributes. Yes or no? We have already seen this. Okay. For example, you can notice that BCNF does not allow this type of dependency. Okay. Look at this functional dependency where you have, okay, just look at this functional dependency where you have non-super key determining prime attribute. Okay, look at this functional dependency. Just look at this functional dependency. Non-super key determining prime attribute. This functional dependency, this is allowed by 3NF. Yes or no? This is allowed by 3NF, but this is not allowed by BCNF. Yes or no? This is not allowed by BCNF. Is this clear? Let me know. Okay, very simple point. So remember, this functional dependency where a non-super key is determining prime attribute, this type of functional dependency is allowed by 3NF, but this is not allowed by BCNF. So who is more strict? Please tell me. See, every functional dependency which is allowed by BCNF, that is also allowed by 3NF. But this type of functional dependency is allowed by 3NF, but this is not allowed by BCNF. So who is more strict? Please tell me. So BCNF is more strict, yes or no? BCNF has more restrictions, I can say. BCNF is more strict, or I can say BCNF has more restrictions. 3NF is more relaxed. Okay, so you can see BCNF is stricter than 3NF. This statement is actually true. What about the second statement? Lossless dependency preserving decomposition into 3NF is always possible for every relation we can get this type of decomposition which is thin enough, lossless and dependency preserving. This type of decomposition we can always get for every relation. So yes, this is also true. This statement is also true. What about this statement? Lossless dependency preserving decomposition into BCNF. This is always possible. That is false. Yes or no? There are some relations for which we cannot get these three properties together. There are some relations for which there is no decomposition which has these three properties together. Okay, so this statement is false. What about the next statement? Any relation with the two attributes is in BCNF. This we have already seen. This statement is also true. So the question is asking which is false statement. The answer will be option C. Is this question clear to everyone? Let me know. Let's move on. Let's solve this GATE 2019 question. Let the set of functional dependencies, these are the set of functional dependencies, hold on relation X PQRS. X is not in BCNF. Suppose X is decomposed into schema Y, Z. This is the decomposition. Now the question is asking these properties of the decomposition. We are having a decomposition of X into Y, Z. Now the question is asking, is this decomposition in BCNF? Basically, Y, Z are they in BCNF? Also, the question is asking, is this decomposition is lossless or dependency preserving? So we have to check all these properties. Now let's check. Okay, see, very simple point. You have this relation X, which has P, Q, R, S. These are the attributes. And what are the functional dependencies? Those are functional dependencies are QR determining S, R determining P, S determining Q. Okay, these are the functional dependencies. Now, what we are doing? We are dividing this X into two sub-relations. Okay, what are the sub-relations? We are doing a decomposition. Remember, the sub-relations are, one sub-relation is Y, which has two attributes. Those are PR. And another sub-relation is Z, that has three attributes, that is QRS. Okay, so very simple. Now, let's check everything. First of all, you tell me, before we check anything, you just tell me what are the projected FDs of relation of sub-relation Y. What are the functional dependencies that are applicable on this sub-relation? Let me know. In this sub-relation, there are only two attributes, P, R. So what are the functional dependencies between P, R? Let me know. Tell me what are the functional dependencies of Y. I can say functional FDs of Y. What are the functional dependencies which are applicable in this subrelation between these two attributes? Which are the functional dependencies? So let's see what P can determine. Tell me. P cannot determine R. Can R determine P? Yes, R can determine P. Okay, P cannot determine R, but R can determine P. Yes or no? So this is the functional dependency of Y. And what are the functional dependencies of Z? What are the functional dependencies which are applicable on this subrelation? Among these attributes, which are the functional dependencies? Tell me all the functional dependencies. Q, R, S. Let's see. Let's start from Q. Can Q determine anything? You can easily see Q cannot determine anything. Let's see this R. Can R determine anything? Let me know. Can R determine anything? R, P. No. R also cannot determine. Focus on these three attributes. R cannot determine any of these attributes. What about S? S can determine Q. Okay, you just find here. You just find what is S plus. S plus will be what? What will be S plus? S plus is SQ. That's it. So S can determine Q. Okay. Now let's take two attributes. What about QR? What about QR? Can it determine S? Yes, QR can determine S. Okay, yes or no? You can see that QR can determine S. Let's take two attributes. What about RS? You can see S can determine Q, so RS can also determine Q. So RS determining Q, that is actually redundant. Yes or no? We already have S determining Q, so we don't have to write this. This is actually redundant. Okay, I can say this is actually redundant because already you can see S is determining Q. So this is actually redundant. What else? For example, QS, can they determine R? QS, can they determine R? Let's look at this. QS plus. QS will be QS. That's it. Yes or no? So these are the functional dependencies of Z. Is this clear? The projected FDs, this type of FDs of sub relations, these are called projected FDs. Yes or no? I told you this. So these are actually the projected FDs of Y. These are the functional dependencies applicable on this subrelation Y. So I can say these are the projected FDs of Y. Or in simple words, you can say these are the functional dependencies of Y and these are the functional dependencies of Z. These are the projected functional dependencies of this relation, subrelation Z. Is this clear? So far, what we got? So we got the functional dependencies. Remember, in this Y, the functional dependencies we have, these are R determining P. These are the functional dependencies. And in this Z, what are the functional dependencies we have? We have S determining Q, also QR determining S. Okay. So now we check all the three properties. First, you tell me, is this decomposition BCNF? Let me know. Here you have nothing to check because only two attributes. Every relation with two attribute is in BCNF. Yes or no? Every relation with two attribute is always in BCNF. So this Y is in BCNF. There is nothing to check. Okay, don't even check because every relation with two attribute is always in BCNF. Y is definitely in BCNF. So there is nothing to check for Y. What about Z? Focus on Z and tell me what are the candidate keys for Z. For Z, what are the candidate keys? Let me know what are the candidate keys for Z. These are the functional dependencies. Now the candidate keys, what are those? You can see QR is a candidate key. Okay, QR is a candidate key and SR is a candidate key. Okay, QR, SR, they are candidate key. So now you can easily see that this is the violation of BCNF. So Z is not in BCNF. Z not in BCNF. Why? What is the violation? Tell me where is the violation? Violation is S determining Q because you can see this S is not a super key. Is this clear? Okay, so very simple. I can say that this decomposition is not in BCNF. Remember, Y is in BCNF, but Z is not in BCNF. So this is the first thing that we got. Okay. So you can see first statement is saying that they are in BCNF. This statement is actually false. False. Okay. Y is in BCNF, but Z is not BCNF. Okay. Let's see the second question now. Now we need to check lossless or not. Let's see the second property, that is lossless or not. Lossless or lossy. For that, what you will do? See, this is a binary decomposition, right? Okay, you already know that this is a binary decomposition because this relation we are dividing into two sub relations. So this is actually a binary decomposition. For binary decomposition, how do we check lossless or lossy? Let me know. For binary decomposition, very simple. In this sub relation, in these two sub relations, find the common set of attributes. Okay, find what is Y intersection Z. Y intersection Z, that is R. Now you find, here you find, in the original relation, you find what is R plus. In the original relation, you find R plus. What that will be? R plus will be RP. That's it. Yes or no? RP. So you can easily see that this R, you can see the common set of attributes is R, and you can see this R can determine the relation Y. Yes or no? Because you can see R can determine P. R plus is RP. So I can say this R is super key in this sub relation Y. Okay, so I can say this is lossless. Is this clear? So this is a lossless because you can see the common set of attributes of these two sub relations, that is super key in one of them. Okay, so you can see this R, this is super key in this sub relation. So this is a lossless decomposition. What about dependency preservation? Tell me what about dependency preservation? Let me know. What about this dependency preservation? So here you can easily see, just focus F1 union F2. Does it cover this F? Okay, let me call it F. Now you just focus F1 union F2. Does it cover F? Okay, now what you need to check? You need to check F1 union F2 covers F or not. Okay, is this clear? So just check F1 union F2, does it cover F or not? That's it. This is what you need to check. So tell me, is this FD covered? In this F1 union F2, okay, remember in this F1 union F2, what you will check? You just find what is QR closer. Okay, in this F1 union F2, what is QR closer? Tell me. In this, what is QR closer? So you can see, yes, QR can determine S. So this is actually covered. Okay, is this clear? Okay, so very simple. If you find the QR closer, that will be QRSP. Okay, in F1 union F2. So yes, this dependency is covered. What about this dependency? Yes, this is also covered. Yes or no? This is also covered. Next, what about this S determining Q? Yes, that is also covered. Right? Yes or no? So did you notice that F1 union F2, does it cover F? This statement is true. Okay. The answer is yes. Is this clear? I hope you understood this, because in F1 union F2, you can find what is QR plus. So in this F1 union F2, QR plus contains S. So this FD is covered. Similarly, this FD is covered here, and this FD is covered here. Okay, so very easily, you can easily see this, that F1 in F2, F1 union F2 covers F. Okay, so dependency preservation, the answer is yes. So that's it. This is the complete analysis of this GATE exam question. Okay, so this second statement is saying that this is lossless and dependency preserving. Okay, so yes, this is dependency preserving, and yes, this is lossless. So this statement is actually true. Okay, so the second statement is true and the first statement is false. Is this clear? For this question, answer is option C. Let me know, did you understand? Let's solve this GATE 1994 question. State true or false with reason. So tell me, is this statement true or false? There is always a decomposition in BCNF that is lossless and dependency preserving. This statement is false. Okay, yes or no? This statement is a false. Now let me give you the reason. Let me give you a relation. I will give you a relation for which there is no decomposition, which will have all these three properties. I will give you a relation which has no BCNF decomposition, satisfying lossless and dependency preservation together. Okay, so now let me give you, so you can consider this relation RABC, a very simple relation, only three attributes, and these are the functional dependencies. Now let me tell you, I will prove it, that for this relation there is no lossless dependency preserving BCNF decomposition. Means if you do BCNF decomposition of this relation, then dependency preservation cannot be satisfied. Okay, whatever BCNF decomposition you do, this dependency preservation will not be satisfied. Okay, so for this relation, there is no decomposition which satisfies all these three properties together: BCNF, lossless, and dependency preservation. Okay, let me prove it to you. So let's quickly see this. First of all, you tell me, is this in BCNF? Let me know. See, these are the functional dependencies. So what are the candidate keys? You tell me about the candidate keys. Here, the candidate keys are AB. AB is a candidate key. Also, CB is a candidate key. Sorry, AC. AB is a candidate key, AC is a candidate key. Yes or no? These are the candidate keys. Now you tell me, is this relation in BCNF? This relation is not in BCNF. Okay. Why this is not in BCNF? This is the violation. Correct? Here you can notice this is the violation. Okay. So very simple, because this C, this is not super key. This is not super key. So this relation is not in BCNF. Now let me tell you that whatever decomposition you do, definitely this dependency will be lost. Okay, see, very simple. What you can do whatever decomposition you want to do, then definitely this dependency will be lost, because just think about it. Okay, let me see, only three attributes are there. So let's check all the decompositions. Let's quickly check all the decomposition. First of all, you tell me, is it possible I can keep all the three attributes together? Is it possible I can keep all the three attributes together in the same relation? That is not possible, because if I keep all of them together in the same relation, then that will not be in BCNF. I want BCNF decomposition. So I cannot keep all of them together. Okay, so now let's consider all the decompositions. Okay, just consider all the, let me consider all decompositions, because only three attributes are there. You can consider all the decomposition. Consider all decompositions. For example, let me consider this type of decomposition where you have R1 has AB and R2 has BC. Okay, now tell me here which FD is lost. Just think about it. Similarly, I can consider this decomposition where you have AC and R2 has BC. Here also one dependency is lost. Another I can consider, you can do whatever you want. For example, another I can consider is what another I can consider. For example, AB and R2 has AC. You can consider this also. Okay. Similarly, you can consider this R1 has only A and R2 has BC. Okay, so basically you can consider any decomposition. In every decomposition, what will happen? See, whatever decomposition you consider, for example, you can consider R1 has A, R2 has B, R3 has C. Okay, you can consider three relations. R1 has A, R2 has B, R3 has C. That also you can consider. But whatever you consider, what will happen? Notice this dependency is gone. Yes or no? In everywhere you can see this dependency is lost. This is a lost. Do you agree? Let me know. In every decomposition, you can easily see this is lost. This is lost. Okay. Is this clear? Please tell me. So you can easily see that for this relation, whatever decomposition I consider, I cannot preserve the I cannot preserve the dependency. A student is saying ABC, comma BC. Okay. A student is saying ABC, comma BC. But this is not even in BCNF. We want BCNF decomposition. This is not even in BCNF. Yes or no? See, this is what I told you, that this relation is not in BCNF. I want BCNF decomposition. I want BCNF decomposition. If you give me ABC, comma BC, if you give me this R1 is not even in BCNF. Okay. Are you getting my point? So remember, whatever decomposition you give me, you can see this dependency will be lost. Whatever BCNF decomposition you give me whatever BCNF decomposition you want. See, this is a BCNF decomposition, this is BCNF decomposition, this is BCNF decomposition, this is BCNF decomposition. All of them are BCNF decomposition. Consider all BCNF decompositions. All of them are BCNF decompositions, remember. And in all of them, this dependency is lost. Is this clear? So remember, this relation has no decomposition which will satisfy BCNF and dependency preservation together. If you satisfy BCNF decomposition, then this property will not be satisfied. Is this clear? Is this example clear? So the reason, if you want, the reason is very simple. Consider this reason. Relation R ABC, and these are the functional dependencies. AB determining C, C determining B. Okay, you can see this relation has no decomposition which will satisfy all these three properties. So this is the complete analysis of this GATE 1994 question. Is this clear? Please tell me, did you understand? Let me know. Now, is this point clear that there are some relations for which satisfying these three properties is not possible? There are some relations for which there is no decomposition which will satisfy BCNF, lossless, dependency preservation, all these three properties together. Okay. So very simple. Now let's move on. Let's solve this GATE 2001 question. Relation RABCD is a relation which of the following does not have a lossless joint dependency preserving BCNF decomposition? This is what we need to find. Okay. See, there are four functional dependencies given to you. Basically, there are four relations given to you. Okay. You have four relations, this relation, and so on. Four relations are given. Now we have to find for which of these relations does not have any decomposition which is lossless and dependency preserving BCNF decomposition. Okay, this is what we need to check. So let's start. Now let me start with the first one. Let me check. Okay, see this first one. The first one has, you have a relation R A B C D. This is your relation, and the functional dependencies are A determining B, B determining C D. First of all, you tell me, is this in BCNF? Let me know. First, you check, is this in BCNF or not? Let me know. See, from here, you can easily see what are the candidate keys. What will be the candidate key? Please tell me. The candidate key is A. So, this is a violation. Yes or no? This is a violation of BCNF. Okay, very simple. So, definitely this relation, this option A, this is not in BCNF. Okay, this is not in BCNF. So, decompose. Yes or no? So, what we will do? So, we will decompose into BCNF. This is what we need to do. Correct? Because this relation is not in BCNF, so we decompose into BCNF. Now let me tell you the BCNF decomposition algorithm. In our lectures we have already seen, but let me quickly tell you again. What is the BCNF decomposition algorithm? Do you remember? Do you remember the BCNF decomposition algorithm? Let me quickly tell you. So if R is not in BCNF, okay, if R is not in BCNF, remember, if R is already in BCNF, then will you decompose? If relation is already in BCNF, then will you decompose? No, there is no need of decomposition. Yes or no? If the relation is already in BCNF, then that relation itself is BCNF, so there is no need of decomposition. Okay, so if R is not in BCNF, then there will be violation. Okay, yes or no? Then take any violation. Very simple, take any violation. Take a violation. Okay, there can be many violations. So what you do, take a violation, any violation you take. For example, this type of violation, X determining A, this type of violation you take. Okay, so here this is a violation, it means this is not a super key, because this is a violation of BCNF, so this is not a super key. Now what you need to do, now you need to find X plus. Basically what you need to do, now you need to decompose. Okay, you need to decompose R into R1 comma R2. Okay, what will be R1, what will be R2? Let me tell you. The R1 will have X plus. Very simple. In the R1, you will put X plus. Okay, find X closure. See, this is the violation. In this violation, what you do? Find the closure of LHS. And what R2 will have? R2 will have, from R, you remove X plus, but you add X. Okay, means you remove this X plus, but you add this X. This LHS you add. Okay, so this is the BCNF decomposition algorithm, very simple algorithm. Okay, so this algorithm you can apply here. Okay, let's apply this algorithm here. So let's decompose into BCNF. So this is the violation we found. Yes or no? So what you will do? Decompose. Very simple. What you will do? You will find B plus. Okay, take violation. Take a violation. So you can easily see that we got this violation B determining CD. Take this violation. Okay, now what you are going to do? You will find B plus. So B plus will be BCD. Okay. Now what you will do? Now this R, now this relation R you will divide into R1 comma R2. What R1 will have? R1 will have this BCD. Okay. I told you that if you have a violation, then you find X plus, you find this X plus. This X plus will be one relation, and the another relation will have all the attributes minus X plus X. Okay, don't remove these attributes. Okay, these X attributes, don't remove them. So very simple here. So this BCD will be going to R1, and in R2 what you will get? In R2, remember, from R remove BCD. From R you remove BCD, what you will get? From R you remove BCD, what you will get? You will get A. Okay, but add this B, add this X. Okay, so finally you will get AB. Now you check. Now what you do? Now you check. Remember, after you do this decomposition, now you check R1, R2 are in BCNF or not. Okay. Now check R1, R2 are in BCNF or not. Okay. Is this clear? If they are not in BCNF, then what you will do? If any of them is not in BCNF, for example, if this is not in BCNF, then what you will do? Then repeat the same procedure. Okay, very simple. Then again decompose, then further decompose. So here you tell me, did we get BCNF? See, this is definitely in BCNF because only two attributes, nothing to check. Every relation with two attribute is in BCNF. So this is definitely in BCNF. Okay, what about this? Is this in BCNF? Yes, this is also in BCNF, right? Okay, this is also in BCNF because in this you only have this FD. Okay, in this R1 you only have this functional dependency. Only this functional dependency we have. So you can see this R1 is also in BCNF, right? And can you notice, is this lossless? Is this lossless? Let me know. Check. Check if it is lossless or not. Please tell me. See, BCNF is done. Now you check lossless or not. Yes, this is lossless. Okay, yes, this is lossless. You can see the set of common attributes is B, and you can see this B is a super key in R1. So this is lossless. Is this dependency preserving? Is this dependency preserving? You can see this dependency is preserved here. This dependency is preserved by R2, and this dependency is preserved by R1. So yes, this is dependency preserving also. Okay, is this clear? So we have done this part A. So this option A, for option A, definitely possible, yes or no? For option A, BCNF decomposition with lossless and with lossless join and dependency preservation possible. Okay, is this clear? So remember, the question is asking does not have. So definitely this is not the answer. Option A is not the answer. Is this clear? Option A is clear to everyone. Please tell me. See, very simple. This is your option A. We already know this is not in BCNF. What we did? First, we are finding is this in BCNF or not? This option A. We found that this is not in BCNF. So what we will do? We will decompose into BCNF. We can apply this BCNF decomposition algorithm. What this algorithm will do? It will take a violation. Take this type of violation of BCNF you take. Then what you do? You find this X plus, that will be your subrelation R1. And in R2, what you will do? You will put from R, you remove this X plus, but you add this X. Okay, but you add this X. Very simple. Then what you will do? You will again check, are they in BCNF? Is this BCNF? Is this BCNF? If they are not in BCNF, for example, if this is not in BCNF, then you will further decompose. Then again, you will do the same procedure. Okay, so this is the BCNF decomposition algorithm. For this option A, we can apply the BCNF decomposition algorithm. This is the violation. This is the violation of BCNF. So we will take this violation and you can see this is the decomposition we will get. Here you can easily see this decomposition. This is lossless. This is dependency preserving. And also this is BCNF. Both are in BCNF. So definitely I can say that for this option A, BCNF decomposition with lossless join and dependency preserving possible. Okay, now let's see option B. Now tell me about option B. Each option we will see one by one. What about this option B? So let's look at option B. We have this relation R, A, B, C, D. And the functional dependencies are A determining B, B determining C, C determining D. These are the functional dependencies. Okay. So first you tell me, is this in BCNF? Let me know. First you check, is this in BCNF or not? What are the candidate keys? See, there is only one candidate key, that is A. So definitely this is not in BCNF. Yes or no? This relation is not in BCNF. Okay, what are the violations? This is violation. This is violation of BCNF because this B is not super key. Similarly, this is violation of BCNF. Because this is not super key. Okay, is this clear? These are violations of BCNF. This is not violation. Okay, yes or no? This is not violation. Because here A is super key. Here you can notice that A is super key. Okay, so what you will do, this relation is not in BCNF, so what are you going to do, please tell me? So decompose R into BCNF. Okay, this is what we need to do, decompose into BCNF. So what you will do, take a violation, take any violation, take a violation. Okay, which violation you will take? Any violation you can take, remember. Okay, for example, you can take whatever violation you want to take. For example, let me take B determining C. Okay, take this violation, take a violation. What you will do, you will find B plus. What is B plus? B plus is BCD. Okay, so now what will happen, this relation you will divide into R1 R2. What R1 will have? R1 will have B plus, R1 will have BCD. What R2 will have? What R2 will have? From this, you remove BCD. What you will get? You will get A. But you add this X, this LHS you add. So you will get finally AB. Okay, is this clear? But here you notice one thing, that this is in BCNF. This is in BCNF, right? Yes or no? This is in BCNF. And what about this? Please tell me, what about this? Is this in BCNF? This is not in BCNF, right? This R1 is not in BCNF. You can easily see. Because in this R1, okay, let me focus on R1. So we got this R1, R2. Remember, R1 we got, that is BCD. This is the R1 we got. And R2 we got is AB. Okay. Now here, this is already in BCNF because only two attributes. So this is in BCNF. Every relation with two attributes is in BCNF. Okay. This is not in BCNF. Why this is not in BCNF? Because just see what are the functional dependencies in R1. In R1, we have B determining C, C determining D. So what are the candidate keys? Candidate key is B. So this is the violation. So this is the violation of BCNF. Now what you will do? Now you will further decompose. Okay, very simple. So take this violation. So take this violation C determining D. Find what is C closure, that is CD. Then what you will do? Then this R1 you will further decompose. Okay, R1 you will further decompose into CD. Yes or no? You will further decompose into CD and BC. Okay, is this clear? Simple. Now you can see this is BCNF. Now you can see this is BCNF. So finally we got BCNF, BCNF. Yes or no? Is this clear? So remember, this was your original relation ABCD. Okay, and these were the functional dependencies. A determining B, this was our original relation. B determining C, C determining D. We got decomposition. Okay, we got R1, R2, R3. R1, what was R1? So you can see basically this is what we got, A, B, C, D, B, C. Okay, we got A, B, C, D, B, C. A, B, B, C, C, D. So this is the decomposition we got. Is this clear? Let me know. We got this decomposition. This is a BCNF decomposition, BCNF. Okay, this is a BCNF decomposition. Now here, this is in BCNF, this is in BCNF, this is in BCNF because every relation with two attribute is in BCNF. Now, can you notice, is this dependency preserving? Is this dependency preserving? This dependency preserved by R1, this dependency preserved by R2, this dependency preserved by R3. Yes or no? So this decomposition, this is dependency preserving. This is dependency preserving. Also, this is lossless. Okay, so this is, you can see all the three properties are there. This is a BCNF. All of them are in BCNF, and dependency is preserved. This dependency preserved by R1, this dependency preserved by R2, this dependency preserved by R3. Yes or no? So you can see, and this is lossless. So all the three properties are satisfied. So again, you can see this has, remember, for this option B, for this relation, what I can say, there exists decomposition. There exists decomposition. Okay, there exists decomposition which will have all the three properties. It will have this property also. It will have lossless property also, and it will have dependency preservation property also. Okay, is this clear? Very simple. What about the next? First, you tell me option D. Let me know about option D. Tell me, what can you do about option D? Tell me, this is your relation R, A, B, C, D, and the functional dependency that is given to you, that is A determining B, C, D. First, what you will do? First, you will check, is this in BCNF or not? Let me know. What are the candidate keys? A is the candidate key. This is already in BCNF. This is already in BCNF. Okay. Is this clear? This is already in BCNF, so there is no decomposition required. Or I can say, this itself is decomposition. This itself. Okay. Basically, either I can say no decomposition required, no BCNF decomposition required. No BCNF decomposition required. Or I can say, that this R itself is BCNF decomposition. This R itself is BCNF decomposition. R itself is BCNF decomposition of R. Correct? Okay. So R is BCNF decomposition of R. So there is no decomposition required. So again, I can say that. Okay, so because no decomposition required, so there is no point of lossy or not preserving decomposition, not preserving the dependencies. Yes or no? So you can see this is in BCNF. Okay, there is no point of lossy. This is already lossless. Okay, this is already lossless, and this is dependency preserving. Yes or no? All the three properties are there for this option D. Okay, very simple. Now, if you are in the GATE exam, then which option you will take? Tell me. If you are in the GATE exam, then the only option that is remaining, that is option C. Yes or no? But now let's see option C. Option C does not have any decomposition which will satisfy all these three properties. Okay, so let's see option C now. The last option is remaining, option C. That is AB determining, this is your relation R, A, B, C, D. And these are the functional dependencies. Functional dependencies are AB determining C and C determining AD. First, you tell me, what are the candidate keys? First, you check, is this in BCNF or not? Okay, for this, you find what are the candidate keys. Tell me what are the candidate keys. You can see AB is a candidate key. BC is a candidate key, right? Yes or no? AB, BC, they are the candidate key in this. Okay, very simple. So tell me, what is the violation then? AB, BC, they are the candidate key. Then what is the violation then? This is the violation. This is the violation of BCNF because C is not super key. This is not super key. Okay, so this is the violation of BCNF. So definitely this option C, this is not in BCNF. Okay, if this is not in BCNF, then what you will do? Then you will decompose. You will decompose into BCNF. Okay, what we will do? We will decompose this relation R into BCNF. This is what we are going to do. Okay, now one thing I want to tell you, you can apply the BCNF decomposition algorithm. Let's apply. Okay, then one important thing I will tell you, how to check whether we can preserve the dependency or not. Okay, that I will tell you. But let's apply the BCNF decomposition algorithm. Okay, just apply the algorithm. Is this clear? So we will decompose into BCNF. Now, if you want to decompose into BCNF, then what you will do? You will apply the algorithm, take a violation. Okay, so let me take a violation. Okay, this is the violation, C determining AD. This is the violation, so take this violation. Now, what you will do? Now you will find C plus. C plus will be what? C plus will be AD. Now, what is your next step? Your next step is this R you will decompose into R1, R2. This R1 will have ACD. And what R2 will have? From R, you remove ACD. So you will get B. Okay, you will get B. But you add this LHS. You add this LHS, so you will get BC. Now, this is in BCNF, there is no doubt. Yes or no? There is no doubt this is in BCNF. What about ACD? What about ACD? Is this in BCNF? Let me know. What about ACD? Is this in BCNF? Yes, this is also in BCNF. Yes or no? This ACD, this is also in BCNF. Okay, you can check. What are the FDs? What are the functional dependencies in ACD? In this R1, what are the functional dependencies? Okay, this is the functional dependency. Correct? Is this clear? Okay, this is the functional dependency. That's it. Now you can easily see that this is in BCNF. This is also in BCNF. This is also in BCNF. Is this lossless? Yeah, this is lossless because the set of common attributes. What is common? C is common. And you can see this C is super key in R1. This C is common and this C is super key in R1. Is the dependency preserving? Is this dependency preserving? No. Which dependency is not preserved? Tell me. You can notice this dependency is gone. AB determining C. This dependency is not preserved, right? Yes or no? R1 union R2, they do not preserve this dependency. Yes or no? Dependency preservation is not there because you can see AB determining C lost. Is this clear? Please tell me. Let me know. Did you understand this? So very simple. We got BCNF decomposition. It is lossless, but you can see this dependency is lost. Okay. Now you might be thinking, see, at this point, can I say there is no decomposition which will have BCNF lossless dependency preservation? Tell me. Tell me. At this point, can I stop and can I say that there is no decomposition which can give me these three properties? BCNF lossless dependency preservation. Can I stop and can I say that there is no such decomposition? I cannot stop because please understand, so far only one algorithm I applied. Please understand, here what I have done, I have applied only one algorithm. See, only BCNF decomposition algorithm I applied. Maybe there is some other decomposition. I hope this point you are understanding. See, here I have applied only one algorithm, only this BCNF decomposition algorithm I applied. Did I check all the decompositions? Did I check all the BCNF decompositions? I did not check. Yes or no? But let me tell you, okay, let me tell you one very interesting point. And using this interesting point, you can easily find out whether some dependency will be preserved or not. Okay, so let me tell you. So here, just look at this. See, first of all, here you can notice that look at this functional dependency. Okay, just look at this functional dependency and tell me this AB determining C. Okay, can AB, see, AB will determine C, that is fine, but can you indirectly determine C? Like AB, can it indirectly determine C? Can it indirectly, transitively, can it determine C? Let me know. AB determines C, but can AB indirectly determine C? Is there any way to indirectly determine C? Means AB determines something, then something determines C. Is there any way? Please tell me. There is no way. Yes or no? Are you getting my point? So AB determines C, and this will happen. This will happen directly, basically without transitivity. Okay, you cannot put anything here. AB determining C. This is the only situation. Means what I'm saying. Please, I am saying that if you want to preserve this dependency, if you want to preserve this FD, then you must have ABC together in the same table. Are you getting my point? Let me know. Okay, see, very simple point that, very simple point. If I want to preserve this dependency, to preserve, okay, in any decomposition, see, very simple point. In any decomposition, whatever decomposition you take, in any decomposition, to preserve this FD, if I want to preserve, sorry, if I want to preserve AB determining C, okay, to preserve AB determining C, we must have A, B, C in same subrelation. Is this clear? Did you understand? Very simple that. Just notice one thing. Can AB determine C transitively? Means transitively can AB determine C? No. You can easily see here. AB cannot determine C transitively. Okay, there is nothing, basically no intermediate person, no intermediate. Okay, yes or no? See, let me give you one example. For example, consider this relation R, where you have, let's assume, A, B, C. Okay, and you have this type of functional dependency. These are the FDs: A determining B, B determining C, A determining C. Okay, now just look at this FD and tell me, look at this FD. To preserve this FD, do I need to put A comma C together? Let's assume I want to preserve this FD. I want to preserve this FD. Do I need to put A comma C together in the same relation? If I want to preserve this FD, do I need to put AC together in the same relation? The answer is no. Why the answer is no? Because I can indirectly preserve this. See, I can transitively preserve this. Are you getting my point? This functional dependency, I can transitively preserve. Transitively, I can preserve. So I do not have to put AC together in the same relation. So very simple, to preserve A determining C, I don't need to put them in the same relation. To preserve A determining C, we don't need to put AC in same relation, in same sub relation. Okay, yes or no? We can transitively preserve this. We can transitively preserve, transitively preserve this A determining C. What you can do? You can you can create one relation where you have AB, and you can create another relation where you have BC. Now you can transitively preserve. A will determine B, B will determine C. So you can transitively preserve this FD. So this is the point I'm trying to tell you. Please focus on this set of FD. This set of FD is given to you. Now you tell me, okay, both the FDs you look. Now you tell me, AB is determining C, that is fine. That is fine. But is it possible I can transitively determine C? Is it possible that AB can transitively determine C? Some intermediate person can you put? Can you put some intermediate person like D? Can you put D here? No, I cannot. Yes or no? So this is the point. So remember, in any decomposition, whatever decomposition I take, in any decomposition, if I want to preserve this, then we must have ABC together. Yes or no? If I want to preserve this, then ABC must be together. Now there is a problem. What is the problem? Tell me, what is the problem now? Now there is a problem. So this is clear that ABC must be together. Okay. Yes or no? A, B, C, D. And these are the functional dependencies you can see. AB determining C, C determining AD. These are the functional dependencies. We agree that if you want to preserve this, I want to preserve this. So ABC must be together. Okay. Else this will be lost. Yes or no? So to preserve this is mandatory. To preserve, this FD, ABC must be together. That is mandatory. ABC, this ABC must be in same relation, must be in same sub relation. That is mandatory. Okay. Else this FD will be lost. Okay. Else this FD will be lost. Okay, correct. Now there is a problem. Now the problem is if ABC together. Now the problem is this. Let me tell you. Now let me tell you the problem. The problem is if ABC together, if you put ABC together, then this will not be BC enough. Okay, then this will not be BC enough. See, if ABC together, then this is not in BC enough. Why? Why this is not in BC enough? Because if ABC together, then you can see AB will determine C. You can see AB will determine C, but C will determine A. Don't forget C determining A. C will determine A. Yes or no? I hope you are finding this interesting that if you put ABC together, then AB will determine C, C will determine A. Now you can easily see that this is not in BC enough because this is not super key. This is not super key. Is this clear? So that's it. So did you understand that if I preserve this, then I will not get BCNF decomposition? Understood? If I preserve this FD, then I will not get BCNF decomposition. If I get BCNF decomposition, then this will be lost. So there is no decomposition, there is no BCNF decomposition which can preserve this. This is what I wanted to prove. I want to prove that there is no BCNF decomposition which can preserve this FD. If you want to preserve this FD, then ABC attributes must be together. But if you put them together, then because of this, this ABC will not be in BCNF. So finally, I can say that for this relation, there is no decomposition. There is no BCNF decomposition. There is no BCNF decomposition exist which can preserve this FD. AB determining C, this FD. Okay. So the question is asking which of the following does not have all these three properties? Okay. So finally, I can say the answer will be option C. So this is your GATE 2021 question, GATE 2001 question. This is your GATE 2001 question. So I hope you understood. Please tell me the complete analysis. Did you understand? Let me know. The analysis of option C, did you understand? Very simple question, remember? Just check each option one by one. For option A, we have BCNF decomposition, which will satisfy all the properties. For option B, we have BCNF decomposition, which will satisfy all the properties. Option D is already in BCNF, so there is nothing to check. Option C does not have any BCNF decomposition, which will preserve this FD. Okay, is this clear? Simple, right? Now, let's solve this GATE 2002 question. Relation R is decomposed using set of functional dependency F, and relation S is decomposed using another set of functional dependencies G. One decomposition is definitely in BCNF, the other decomposition is definitely in 3NF, but is not known which is which. See, one decomposition is BCNF, another is 3NF, but we don't know which decomposition is which. To make a guaranteed identification, we want to make a guaranteed identification, which decomposition is BCNF, which is 3NF. We want to make a guaranteed identification. Then which of the following tests should be used? Which of the following tests should be used? Dependency preservation, lossless, BCNF definition, and 3NF definition. So understand this question very simple. We have two relations. There is relation R, there is relation S. In this relation R, there are functional dependencies. The set of functional dependencies is F, and here the set of functional dependency is G. Now what you are doing? You are decomposing this. We decompose this. Let's call it D1. And here also we decompose. Okay, we decompose. Let's call it D2. Now the question is saying one of them is in BCNF, another is in 3NF. We don't know which of them is in BCNF, which is in 3NF. Is this clear? See, relation R is decomposed and relation S is decomposed. Okay. One decomposition is in BCNF, another decomposition is in 3NF. It is not known which is which. Then which test we should apply? Which test we should apply for guaranteed identification? So these are the decompositions. This decomposition and this decomposition. One of them is 3NF decomposition, another is BCNF decomposition. Okay, so let's see each option one by one. Tell me, dependency preservation. If I check dependency preservation here, if I check dependency preservation here, then can I find out which is 3NF decomposition, which is BCNF decomposition? Tell me. Let me know. For example, see, both can be dependency preserving. Yes or no? Both can be dependency preserving, right? Okay. Maybe both are dependency preserving, or maybe none of them is dependency preserving, or maybe one of them is dependency preserving, another is not dependency preserving. Whatever case you take, we cannot guarantee which is 3NF, which is BCNF. Yes or no? See, if you apply this test, let's apply this test one. Test one is dependency preservation. dependency preservation test. Now you notice one thing. If both satisfy, if both preserve the dependencies, then also we cannot say anything. If one of them satisfy dependency preservation, another does not satisfy dependency preservation, then also we cannot say anything. And if both of them do not satisfy dependency preservation, then also we cannot say anything. Yes or no? So dependency preservation, whatever be the result, we cannot find out which is 3NF, which is BCNF. Yes or no? Cannot, cannot, cannot be used to find out 3NF or BCNF. Yes or no? Cannot be used to find out which is 3NF, which is BCNF. Is this clear? Is this point clear to everyone? See, one thing, one misconception I want to tell here. Actually, some students, they think that 3NF decomposition will always be dependency preserving. See, one of them is 3NF decomposition, right? And some students, they think that 3NF decomposition will always be dependency preserving. Okay, that is not true. 3NF decomposition may or may not be dependency preserving. Similarly, BCNF decomposition may or may not be dependency preserving. Okay, yes or no? So we don't know whether dependency is preserved or not. Maybe both of them preserve the dependency. Maybe none of them dependency preserving. Maybe one of them is dependency preserving, another is not dependency preserving. But basically, in any case, we cannot say that which is 3NF, which is BCNF. Is this clear? Similarly, lossless. Similarly, lossless. Maybe both are lossless. Maybe both are lossy. Maybe one of them is lossy, another is lossless. Again, we cannot say which is 3NF, which is BCNF. Yes or no? Yes or no? Is this clear? Maybe both are lossless. Maybe both are lossy. Maybe one of them is lossy, another is lossless. But this information does not tell you which is 3NF, which is BCNF. Okay, one is guaranteed to be 3NF, one is guaranteed to be BCNF. Now you tell me about this. What about 3NF definition? See, notice. One of them is 3NF, one of them is BCNF, but both will satisfy 3NF definition. Yes or no? One of them is 3NF, one of them is BCNF, but both of them will satisfy 3NF definition because every BCNF is 3NF. Okay, every 3NF is 3NF, every BCNF is 3NF. So both of them will satisfy this 3NF definition. So this will be satisfied by both. So I can say both will satisfy. Both will satisfy this. Okay, but there is, see, notice this option C. Only BCNF decomposition will satisfy this. Yes or no? Only BCNF one will satisfy this. So this test I can apply. Do you agree? We can check for BCNF. Only BCNF decomposition will satisfy this. Okay, so the decomposition which will satisfy this, that is your BCNF decomposition, and the other one is 3NF decomposition. Okay, so you just check which of them is BCNF. You just apply the BCNF definition. Only the BCNF decomposition will satisfy BCNF definition. The another will be 3NF. So yes, this test we can apply. Okay, remember these two. Remember these two may or may not be satisfied. May or may not be satisfied by any of them. May or may not be satisfied by any of them. Okay, is this clear? So the answer will be option C. This is the only answer. Let's move on. Let's solve this question. This is nearly 2018 question. Tell me the answer. Identify the true statements. Lossless dependency preserving decomposition in 3NF is always possible. Yes, that is correct. This type of decomposition is always possible. Any relation with two attribute is in BCNF. This is also true. Both the statements are true. So 1 and 2 both are true. Let's solve this question. This is nearly 2016 question. Tell me the answer. Every BCNF decomposition is. Every BCNF decomposition is. Can I say every BCNF decomposition is dependency preserving? No. Can I say every BCNF decomposition is not dependency preserving? No. It need be dependency preserving? No. So the answer will be none of these. Answer will be option D. Yes or no? Is this clear? See, every BCNF decomposition is not dependency preserving. That is false. Yes or no? Some BCN of decomposition will be dependency preserving. Some BCN of decomposition will not be dependency preserving. Okay. So finally, for this question, the answer will be option D. Now, let's solve this NILIT 2017 question. This is an interesting question. Actually, this is a very poorly framed question. Remember, this is a NILIT exam question. This is not GATE exam question. This type of question can never come in the GATE exam because this is very poorly framed. The question maker does not have proper understanding of these concepts. Okay. So let's see this. Which one of the following statement is not correct? 3N of decomposition is always lossless and dependency preserving. Is this true statement? 3N of decomposition is always lossless and dependency preserving. This is false. Yes or no? This is also false. This is also false. This is also false. All the statements are actually false. Let me tell you, this question I sent to all the professors, Professor Korth, Nawate, Sudarshan, Professor Sudarshan. Okay, to all the professors, this is the question I sent. Did you notice? This NILIT question I sent to all the professors. You can see this NILIT 2017 question I sent. This was my mail. This was my mail. Okay, I sent this mail. So in this mail, I had put this link and I was asking, I I told that I think no statement is correct. This was my opinion that no statement is correct. Okay. So now let's see their reply. You can see Professor Sudarshan. Their reply was yes, you are correct. Yes, you are right. Okay, you can see. So yes, you are right. There are decompositions that are lossy but in BCNF. Okay, that are lossy but in BCNF. For example, you can do binary decomposition. Okay, you can do decomposition into binary relations. Okay, so very simple. Another reply you can see from the Professor Nawate. Professor Nawate also then saying the same thing. See, if the question is talking about any decomposition, then you are right. Look at this question and tell me, is this question talking about every 3n of decomposition or some 3n of decomposition? Read the statement 1. Read statement S1 and tell me, this statement S1, is this talking about every 3n of decomposition or is this talking about some 3n of decomposition? Yes, this is talking about every 3n of decomposition. So this is the reply from Professor Nawate. You can see, if it is any decomposition, then you are right, then I am right. But if this is a correct decomposition, means if this is a valid, good design decomposition, okay, if this is a good decomposition, because remember, if your decomposition is good decomposition, then it will satisfy lossless property, it will satisfy dependency preservation property. Yes or no? That is a good design. Okay, so this is the reply you can see. So finally, anyway, remember this question will never come in the GATE exam because the GATE professors, they understand the concept. Did you notice in the GATE exam this type of statement has never come? In the GATE exam, we have done all the GATE exam question. Did you notice all the GATE exam question, they are talking about possibility, that it is possible, there exist. Yes or no? Did you notice each and every GATE exam question is talking about the possibility, or each and every GATE exam question is talking about the there exists a decomposition, there exists some decomposition. Okay, so those were the GATE exam question. GATE exam question are always very nice. Those are created by the IIT professors, IIT, IISc professors. They understand the concepts. So you can see all the GATE exam questions, those were very nice. But this is a NILIT exam question. A lot of questions in the NILIT exam are very poor, very poorly framed questions. This is one similar question. Actually, for this question, no option is correct. All the statements are actually false. Okay. Remember, don't worry. This question will never come in the GATE exam, and all the statements are actually false. But tell me, the question maker of the NILIT exam, this question maker, what do you think? What is running in the question maker's mind? If you are attempting the NILIT exam, don't worry about the GATE exam. But if you attempt the NILIT exam and this question comes in front of you, then what the answer you will give? Okay, then the answer you will give is basically, of course, the question maker is thinking that this is true and this is true. Yes or no? The question maker is thinking this is true, this is true. Correct. Okay. The question maker is thinking that S1, S4 are true. It is asking not correct. So S2, S3 not correct. Is this clear? Let me know. Okay. So again, I'm telling you, this is a poorly framed question. And remember, this is not a GATE question. This is NILIT question. This question is not created by a professor. Okay. So this is a poorly framed question, and this type of question will never come in the GATE exam. But If you are attempting NEET exam and this question comes in front of you, then you can put this option. The question is asking not correct, so S2 S3 not correct. Okay, but the actual concept I hope you understood. You can see this is the actual concept, that decomposition can be lossy but in BCNF. You can see decomposition can be lossy but BCNF. This is the actual concept. Okay, so that's it. Finally, one last point I want to discuss, that is which normal form is nice and preferred. Which normal form is preferred? 3NF, BCNF, 2NF. Which normal form is overall preferred? In the real life, in the real database, which normal form is preferred? The answer is 3NF. The answer is 3NF. Let me tell you the reason. See, what benefit BCNF will give you over 3NF? Just tell me this point. BCNF will give you what benefit over 3NF? The only benefit will be some redundancy will be less. Yes or no? BCNF will give you some less redundancy. 3NF has more redundancy and BCNF has somewhat less redundancy. So redundancy will be less in BCNF. Yes or no? But remember, which you will in your laptop also, in your real life also, tell me which of these things you will prefer. Will you prefer losing functional dependencies, or will you prefer, okay, little bit redundancy? See, on one side you are getting little bit more redundancy, on another side you are losing functional dependency. Which you will prefer? Just think about it. What is your opinion? Let me know. On one side you are losing functional dependencies. Will you prefer that? You are losing functional dependencies. Will you prefer that? You will not prefer that, right? You can allow little bit redundancy. Little bit redundancy you can allow. Okay, so that is the reason. Remember that 3NF is the 3NF is preferred. So you can see this is the reason. See, it is not always possible to have a BCNF design that is also dependency preserving. We have already seen. We have already seen that for many relations, it is not always possible to have a BCNF dependency, BCNF design which is dependency preserving. That is the reason. That is the reason people give up on 3 BCNF. People prefer 3NF. Okay, 3NF is preferred over BCNF, and this is the reason. This is the reason. It is always possible to have a 3NF design that is dependency preserving. Yes or no? It is always possible. It is always possible to have a 3NF design which is dependency preserving. So that is the reason. Remember, 3NF is preferred. You can see here in this chart, you can see that will you lose FD? In 3NF, you will never lose FD. You can see, but in BCNF, you can lose FD. Yes or no? Next, you can see that redundancy. In BCNF, there is no redundancy due to FD, but in BCNF, there is redundancy due to MVD. We have already seen in our lectures. I will put the link in the description so you can check it out. If this point is not clear, then you can watch the video. I will provide the link in the description so you can check it out. So you can see BCNF has redundancy. Don't say that BCNF has no redundancy. Remember, BCNF has no redundancy due to FD. You can see BCNF is 100% free from redundancy caused by functional dependency. But BCNF has redundancy because of MVD. Okay. So remember, if let's assume you have BCNF design. If you have BCNF design, then it does not mean you don't have redundancy. BCNF also has redundancy. Okay. So that is the reason 3NF is preferred. Because in the 3NF, at least you will not lose the FD. At least functional dependencies you will not lose. So that is the reason. Remember, 3NF is preferred. So finally, for this question, the answer is which normal form is overall preferred, overall nice? The answer is 3NF, because there is always a possibility to create dependency preserving 3NF decomposition. For any relation, you can create a decomposition in 3NF which is dependency preserving. Okay, so as I told you, this is the reason. You can read this. It is always possible to produce a 3NF design that is dependency preserving. This is the reason 3NF is preferred. Okay, very simple. Now tell me the answer for this GATE exam question, GATE 1998. Which normal form is considered? Which normal form is considered adequate for normal relational database design? The answer is 3NF. Okay, this is considered adequate. So the answer is 3NF. Very simple. Let's solve this UGC NET exam question. Which normal form is considered adequate? The answer is 3NF. Okay. So that's it. This is your chapter. I hope you understood everything. We have done a lot of GATE exam question. I hope you understood the misconception. I hope you got the clarity. And we have done each and every GATE question based on this concept. Each and every GATE question, NEET exam question, UGC NET exam question. So all the questions that are available in the previous exams, each of them we have done with complete analysis. I hope you found this session helpful. Please tell me, did you like this session? Let me know. Let me know. So thank you, everyone. A student is saying that query will take more time if the database is in BCNF. That is usually correct. Not always. That is usually correct. Okay. Actually, remember, normal forms, BCNF, 3NF, these are why they were proposed. Okay, just think about it. Why the proposal of normal forms was given? This 3NF, BCNF, why we study these? We study them just to reduce the anomalies, the insertion anomaly, update anomaly, okay, deletion anomaly. So we want to reduce these anomalies, and to reduce these anomalies, we need to reduce the redundancy. So remember the main motive. If someone asks you what is the main objective of the normal form, that is to reduce the redundancy so that we can reduce the anomalies. Okay, other things are not the objective. Okay, saving the time, these were not the objective. But remember, usually if your relation is in BCNF, then there will be usually more tables. Okay, you will have more number of relations. So the query, if you write a query, then usually it will take more time. In 3NF it will take less time. Just think about it. If you have a single table, then any query will take less time. But if you have many multiple tables, if your query has to search multiple tables, if you have to combine multiple tables to get the answer, then it will take more time. Okay, but again I'm telling you that the objective of BCNF, or I can say the objective of normal form, that is not to save time. The objective of normal form is to reduce the redundancy so that we can reduce the anomalies. That is the main objective of the normal forms. Okay. Okay, thank you, everyone.